Before we get started, I would like to throw a little caveat out there. I am not a physicist, let alone a cosmologist. I am just a science student who happens to be studying biology of all things. Why then would I bother making a video on the Big Bang that probably is not 100% accurate? Simple. I was challenged by a creationist friend of mine who, needless to say, thinks that the Big Bang is a fairy tale. What I have done in this video is to try to explain the Big Bang to the best of my understanding, and for this very reason, I invite anyone out there to correct the mistakes encountered in this video. I am reasonably sure, however, that the information contained herein is, for the most part, sound. So, without any further ado, let us begin. Before we talk about the evidence for the Big Bang, it is important that we spend some time discussing its theoretical foundations, and there are only two. First, there is the cosmological principle, which conjectures that matter is uniformly distributed throughout the universe. Second, there is the theory of general relativity, which tells us that matter curves space, and space dictates the movement of matter. When these two concepts merge, we realize that, if we take the cosmological principle as our starting point and then apply to it the theory of general relativity, the universe suddenly becomes dynamic, either collapsing under its own weight or expanding. While it is perfectly valid to assume that the universe is collapsing due to universal gravitation, scientists understand that to merely assume something to be the case without bothering to look for the actual evidence, rightly so, makes an ass out of you and out of me. This preamble now brings us to the part where we discuss the evidence for the Big Bang, oftentimes referred to as the pillars of the Big Bang. The first line of evidence comes from observations that tell us that, unlike what we may have assumed, the universe is indeed expanding. So, how do we know this universal expansion to be true? To answer this question, we need first consider the electromagnetic spectrum. The wavelength of any type of light is the distance over which the shape of the wave repeats, and it is denoted by the Greek letter lambda. The double-ended arrows here represent the wavelength lambda. The shorter the wavelength is, the hotter and more energetic the light will be, and conversely, the longer the wavelength is, the colder and less energetic it will be. When scientists observe distant sources of light, distant galaxies for instance, they notice that their wavelengths are stretched. In this case, they say that the light is shifted to the red end of the visible region of the electromagnetic spectrum, or simply redshifted. And the farther the emitting source is, the greater this redshift will be. This is due to the fact that the very medium in which light travels is expanding, and as a result, light is being stretched. This medium is space. Space is expanding. Consider these figures. At any given time, the distances between the stars are fixed. Sometime later, these gaps will have increased due to universal expansion. Still further into the future, and the distances separating the stars will have increased yet more. If it can be said that the distance between us, or any other point of reference for that matter, and any other distant galaxy is increasing, then surely, if we were to run the clock backwards, we would see that the universe is getting smaller and smaller and smaller. Our picture of the Big Bang is shaping up. On to the next line of evidence for the Big Bang, the abundance of light elements, namely hydrogen and helium. This is the periodic table. It tabulates the elements or atoms according to their atomic number, the number of protons in a nucleus. Different atoms will absorb different wavelengths of light, producing an absorption spectrum. Here, we have the absorption spectra of hydrogen, helium, lithium, and oxygen, and the technique used to determine these absorption spectra is known as spectroscopy. By using spectroscopy to study distant gas clouds, we can, therefore, determine their composition, that is, we can know which atoms they contain. According to the Big Bang, we should expect to see within these ancient gas clouds about 75% hydrogen and about 25% helium. So what does spectroscopy tell us when we actually assess these pristine gas clouds? You guessed it, we find that they contain about 75% hydrogen and 25% helium. When the Big Bang occurred, it was initially too hot for matter to form. Protons, electrons, and neutrons could not have coalesced into atoms. Some 380,000 years later, as the universal expansion ensued, the temperature decreased to the point where matter could now form. But why just hydrogen and helium? Heavier elements contain more than 2 neutrons in their nuclei, and neutrons decay in a span of about 10 minutes, forming protons and electrons. Therefore, only the simplest and lightest of the elements could have formed in the beginning. Not only does the Big Bang predict this, but, as mentioned earlier, it also gets their observed abundances as detected by spectroscopy right. But wait, there is more. Not all the energy of the early universe went into creating matter. In fact, another prediction made by the Big Bang theory is that this remaining energy should still be observable today as the cosmic microwave background radiation, the afterglow of the Big Bang. When the universe was in its infancy, protons, electrons, and neutrons had not yet coalesced into atoms. This was a time when these subatomic particles formed what is known as plasma, or ionized gas. In the presence of this thick plasma, light could not have moved freely. In a way, light was imprisoned. Once the temperature of the universe had decreased enough, light elements formed. Notice the hydrogen and helium atoms in this image. At this point, light decoupled from plasma. Here, the beams represent this escaping light. If the Big Bang theory is correct, we should be able to observe this very light coming at us from all directions. And we have. This is what it looks like. The cosmic microwave background radiation, the holy grail of cosmology. So far.